it pops up. Pops up here, so that's good. I can close it here. Oh, no. Okay. Now what do I do now? There we go. I just want to close this because it will.
I see.
So let's just reject all those. Should go live. There we go. Pops up here, so that's good. I can close it here. So now I've closed it. It won't echo anymore.
I see.
But they can hear us.
Okay. Hello.
Hello, everyone. Welcome to the Royal Astronomical Society. We're going to start in about, I think, 10 minutes.
Push the map button.
Yeah, that's true. But that's for people Hello, everyone, and welcome to the Royal Astronomical Society. My name is Lucinda Offer. I'm one of the Education Outreach Officers here today to welcome our speaker for December. And it's been a bit of a tradition every year now, since JWST launched in Christmas, to have an update on December. So this is, I think, our third year focused just on JWST, and it's so exciting to see all the beautiful new imagery that comes off that space telescope. And we feel very fortunate to have Dr. Rowe-Gurney with us here today. So Naomi Rowe-Gurney is an Equity, Diversity, and Inclusion Support Officer here at the Royal Astronomical Society. She will be helping us with a number of projects in the astronomy sector. And she's also a research development manager for the UK Centre for Ecology and Hydrology. And she just completed a contract as a planetary scientist at NASA Goddard Space Flight Center, where she worked on JWST. And she was a research coordinator for the JWST Solar System Team, and her own research focused on the atmosphere of the ice giants like Uranus and Neptune. Naomi has led a Hubble Space Telescope program designed to support ice giant JWST observations. And she obtained her PhD in 2021 from the University of Leicester. And throughout her PhD and postdoc, Naomi has used her past experience as a teacher to partake in significant science communication work and considerable equity, diversity, and inclusion work promoting science to underrepresented groups. Please, let's welcome Dr. Rowe-Gurney. Thank you.
Thank you so much. Hello to everyone in the room. Thank you for being here, and hello to everyone online. I can't see you, but I know you're there. Okay, so today I'm going to talk to you about JWST and its first 2 years. So I was lucky enough to be directly involved with it over these last 2 years, and I only just got back recently from that position. So I'll start with a little bit more about me and my career. So I started my journey doing a 4-year integrated master's in physics with astrophysics at the University of Leicester. And then I ended up back in Leicester for my PhD. And my thesis was looking at the atmospheres of Uranus and Neptune from the Spitzer Space Telescope, which I'll talk about more in a second. And when I got my PhD, I moved out to the US and near Washington, DC area. And I was a research coordinator for the Team Solar System at NASA Goddard Space Flight Center. So that was kind of a postdoc. But it was an unconventional postdoc because a lot of it was working with other science teams rather than doing my own science. I got back about 2 months ago, so in October. And now I'm here at the RAS doing EDI work and also at the UKCEH or Centre for Ecology and Hydrology, supporting research into environmental science. So this is probably, this and the 6 p.m. talk are probably one of my last talks talking about JWST, which is kind of sad. So what is the JWST? So I'm going to start at the beginning and talk about the fact that it's the largest and the most powerful telescope that we've ever sent to space. It has a 6.5 meter primary mirror made of 18 separate gold-plated segments. And then it has 4 scientific instruments that are all housed behind the mirror, and they work in infrared wavelengths. And it also has a tennis court-sized 5-layer sun shield that keeps it cool. And it was mostly built for looking at distant astrophysical things like galaxies, stars, and nebulas. But very early on in its concept phase, scientists also wanted to be able to look at solar system objects. So this right image here shows a very early concept design for what it used to be called, which was the Next Generation Space Telescope, or the NGST. And scientists did this sketch at Goddard, and it shows a lot of similarities to what we actually know as JWST today. It has that large deployable mirror, an open telescope design, and a large multi-layered sun shield. And it took worldwide collaboration to get to the point we're at now to achieve this huge advancement for astronomy. So NASA was part of it in the US. The Canadian Space Agency were also a member, and also the European Space Agency, including the UK. The UK had a huge input into the structural design of the telescope, and also one of the instruments, which I'll talk about later, the mid-infrared instrument, which is one of the most powerful, and that was also led by the team in the UK. So a lot of people say that JWST is the successor to the Hubble Space Telescope, but that would be a disservice to Hubble, because when it comes to telescopes, Hubble is still the most famous space telescope we have, although JWST is catching up slowly. But Hubble's been around a lot longer than JWST has, and it's still going strong today. It was launched in 1990. It's actually about 2 months older than me. And in that time, it's done over 1.5 million observations, and it's produced gorgeous images like the ones here, especially of the solar system. So it also has this thing where it looks at distant objects, but also looks at things in our own solar system as well. And the animation here shows just how huge both of these are, with a person there for scale. And JWST's mirror has an area more than 5 times greater than Hubble Space Telescopes. And Hubble and JWST really complement each other, and they've been working together very efficiently to look at objects that I will talk about in a moment. And they're good at working together because they have a key difference, and that's in their different wavelength bands. So Hubble sees mostly in visible wavelengths, whereas JWST looks at longer wavelengths that are beyond red in the spectrum. And these are called infrared, and we experience this range as heat. So JWST is like a really, really expensive night vision camera. It's split right down the center of this screen here. Everything on the left side is the visible in Hubble, from Hubble, and everything on the right side is infrared from JWST. And so you can see in the background the famous pillars of creation that show how we can see through the cold dust and the gassy hot stars using the infrared. And we can also see features for planetary science. We can see different things. We can see through those hazes and see different altitudes and features in the atmosphere using infrared. So the features in the right of this Jupiter image, you can see in the left one, some things are visible in some are invisible in others. So both images are useful for looking at different things. So another space telescope that uses infrared was Spitzer. Spitzer was actually the predecessor to JWST because it was decommissioned in January 2020, just in time for JWST to go up. And it was launched in the same generation of telescopes as Hubble in 2003. And it was in an Earth trailing orbit, so it's following us around the sun. And it's very, very small compared to the other two, with the mirror being less than a meter across. And for telescopes, that means something because a bigger mirror means we can collect more photons. So more photons means we can look at dimmer, smaller, colder, more distant objects. And JWST's mirror has an area more than 45 times greater than Spitzer's. And one of my favorite facts is that the Spitzer mirror is actually the same size as the secondary mirror on the JWST. So that mirror that's on the end of the boom that reflects light back into the instruments is the same size as the Spitzer mirror was. And my PhD research used Spitzer to look at Uranus and Neptune in preparation for JWST. So how does a space telescope like JWST work? It works like any telescope that you have in your lounge that you use in the back garden. Its main job is to look at things that are really distant. And JWST gathers light from these distant objects and focuses it into its instruments. So instead of your eye, it's focusing it onto sensors and detectors. And those instruments are housed behind the mirror. And those 18 gold hexagonal segments, they're all able to move completely independently and remotely so that we can adjust the focus at any time. And once that light is focused into the instruments, JWST stores that observational data. But then we have to get the data from 1.5 million kilometers away all the way back to Earth. And that's where something called the Deep Space Network comes in, or the DSN. And that's a number of huge dishes located all around the world that receive this data. And then once they receive it, they send it through to a place called the Space Telescope Science Institute, or the STSCI, who process it and store it so that scientists can access it. So the Space Telescope Science Institute, or STSCI, is located in Baltimore. So it's just up the road from Goddard Space Flight Center and Washington, D.C. And it plays a very pivotal role in JWST. And I already mentioned that they kind of store and distribute the data that comes down from the telescope, but it's also home to the JWST operational control room. So where they operate the observatory from and all of the instruments. And there's a picture of myself here with my colleague Ian outside the room last year. And they do not let you inside the operational control room, no matter how much you ask them. And the STSCI scientists, they analyze a lot of the data that they produce, and they give us lots of the exciting kind of public releases that you might have seen that comes directly from Space Telescope. And they also did a lot of the commissioning, so getting the telescope ready for science. I'll talk about commissioning more in a moment. So going back to the telescope itself, the power of JWST isn't just in the size of the mirror, it's also in the instruments. So there are 4 instruments aboard, all housed behind that mirror in something called the ISIM, or the Integrated Science Instrument Module. And so these 4 instruments are the FGS NIRIS, the near-infrared camera, or NIRCam, the near-infrared spectrograph, or NIRSpec, the mid-infrared instrument, MIRI. And these instruments provide imaging and spectroscopic capabilities across the whole spectral range. And the instruments that begin with near are in the near-infrared, and that's at shorter wavelengths closer to red in the spectrum. And then MIRI is the only one that works in the mid-infrared, that is at longer wavelengths. And MIRI and NIRSpec are also really exciting because they do something called spectroscopy, which is extremely powerful. And imaging is always easier to explain because our cameras on our phones do imaging, our own eyes do imaging all the time. So talking about spectra is a little bit harder, but it's really exciting for scientists And JWST has 6 different spectroscopic modes, but the main principle of spectroscopy and behind all of the modes is that we're splitting up the light into different wavelengths. And we measure how much light there is at each of these wavelengths, and that gives us a spectrum like the plot you can see in the top right. And this spectrum at the top shows the molecules that may be detected in a star-forming region, like in the Eagle Nebula. And the most exciting spectroscopic mode for solar system scientists particularly is this IFU mode, or integral field unit mode. And an IFU means we don't have to choose anymore whether we get an image or a spectrum, we can get both at the same time. So each pixel in the image that you take has a spectrum that you can analyze. So it's extremely powerful, and it generates these things called image cubes, because we have 3 dimensions of information instead of 2. And we'll see how useful that is in a moment. And it's hard to believe that all these images were released just last year in these first image releases that they did. But they're very useful for reminding us about JWST's 4 major science themes and the whole reason that it was built in the first place. So the first one, first light, so looking extremely far away at the early universe. The second one is understanding our galaxies. And the third one is seeing through that dust and gas to look at where stars are being born. So all stuff that's extremely, extremely distant. And if we come a little bit closer and we look at this 4th science theme, we're looking, a little bit closer, but a lot of people think when they think of planetary systems and the origin of life, they still automatically think of exoplanets. But there's no better way to understand a planetary system than by understanding our own planetary system that we live in. So solar system science with JWST is a very large and very important area. And around 7% of JWST's first year of observations was devoted entirely to the solar system. So what in the solar system can JWST look at? It can observe everything from Mars out, planets, moons, asteroids, Kuiper Belt objects, comets. And engineers had to overcome some obstacles to make this all possible, because galaxies and stars and nebulas, everything distant, is very dim in comparison and also very stationary on the night sky, whereas everything in the solar system is extremely bright compared to that and also moving. And so they had to make sure that JWST can track these objects when it's moving and also make sure that it doesn't break when it looks at something bright. And the process of commissioning means that everything leading up to science, so from launch all the way through to science. So it took 6 months to get the telescope ready to do its job. And JWST has had 3 phases of this instrument commissioning phase. And the first phase was spacecraft commissioning, which means launch, deployment, beginning of cooling to operating temperatures. The second phase was telescope commissioning, so aligning the mirrors and all the optics. And then the third phase was scientific instrument commissioning, so calibration and characterization of those 4 instruments. And the hardest and most nerve-wracking part was definitely phase 1. Every scientist, every engineer that worked on it was having a panic attack that Christmas morning. And unfortunately, because of COVID, we all had to be relegated to our own homes to have those panic attacks. So it was extremely terrifying, but there's a picture of me very early in the morning in my pajamas, watching the live stream, very, very anxious, but it went absolutely perfectly. And all phases of the launch went off without a hitch. And that was thanks to ESA and their Ariane 5 team. And that means that there's enough fuel for the mission for another 20 years, which is optimum. And this lower right corner here shows the last time we could view the telescope before it started its long journey. So this was like the last picture of JWST that we could take. So it took an entire agonizing month of constant deployments to reach its home out at the L2 Lagrange point. L2 is a gravity well that JWST orbits. It's 1.5 million kilometers away, or about 1 million miles away from Earth. And it kind of follows Earth around the sun. So we're never out of communication with JWST, but it's also far enough away that the heat of Earth doesn't interfere with any of the instruments. And the biggest and most exciting day for me was definitely the secondary mirror deployment. So when that boom folded out, because that up until that point, we couldn't even call it a telescope because it wasn't collecting any light. But as soon as that boom came out, we could collect light. No matter what happened next, it was already a telescope. And then the second phase was telescope commissioning or mirror alignment. This is where we're using the ability to move those 18 separate hexagonal segments to make it a single high precision optical surface and focus that light on each of the 4 instruments. And the aim was to get the light from a star as focused as possible, like the one in this image. And we can see the before and after alignment mirror selfies. So I said the previous picture was like the last photo of JWST, but actually it can take photos of itself, sort of. And that's what comes out when you take a photo of the mirror alignment. So you can see it's definitely better after than it was before. And we can see how important it was to move all those 18 separate segments remotely and independently to achieve this level of focus. And this image here shows all 4 of the instruments with their light successfully focused and ready for this last instrument commissioning phase to begin. And I was involved in a team during this phase that did a part of the process, and it was led by astronomers at Space Telescope Science Institute. And we did 2 things that are important for solar system observations. We did something called moving target or MT testing, where we make sure that JWST can track different objects. And we also did something called scattered light testing, where we make sure that it doesn't break when it looks at something bright. So checking those solar system specific requirements. So the first test was the moving target testing. So when observing objects in the solar system, we need the observatory to change its pointing direction relative to the background guide stars during the observation. So it's a very intensely engineering heavy thing that we have to do. And the software also has to be able to deal with it. And so we have to find out how fast can JWST actually do this process. So we tested this capability by observing asteroids of different apparent speeds using each instrument. And these images are some of the asteroids that we observed for the testing. And our initial speed limit, or the limit that we initially thought JWST could handle, was around 30 milliarc seconds per second, which is the speed unit that we use. And you can see the asteroid in the middle there is speeding. It's going at 67 milliarc seconds per second, so over twice the amount that we thought we would be capable of. But you can see in that bottom left quadrant, that bright point of light that isn't moving, that's the asteroid. So we're successfully tracking that asteroid. As a result, we've been able to increase the speed limit for future observations, and I'll show a great example of that in a moment. So the other type of testing was scattered light testing. So we wanted to answer some fundamental questions like what happens if we look at something really bright like Jupiter? What happens if we look at something that's close by to Jupiter? Will the light like bleed into the instruments? How much will it bleed in? Can the functions all still work? Will it still produce an image? So we tested all these questions and happened to get these Jupiter images. And these were the first images of a planet with JWST, and they shocked everyone because the rings of Jupiter, which can be easily viewed here, are not an easy thing to view. And we did it here with just an instrument test. So it was a great sign of planetary science to come. So we usually split the solar system into 2 distinct areas, planetary systems, so the planets themselves, rings and moons, and then anything that doesn't fall into that category gets to go into small bodies, so asteroids, comets, dwarf planets like Pluto. And during my time at Goddard, I was supporting the planetary systems science teams, and my colleague Ian, who you saw in the picture before, he was supporting the small bodies teams. So studying all of these objects is really important for answering some of the most fundamental questions that we have about the universe. Small bodies, for example, are of huge scientific interest because they're the leftovers from the formation of the solar system. And they likely contain answers about how our solar system itself was formed and how Earth itself was formed. And they may even give us clues as to the origins of life on Earth. And then studying planetary systems is also really important because we get a better understanding of how different types of planets are formed throughout the universe. We want to know about their surfaces, their atmospheres, their clouds, weather differences, composition. And we also want to look at their rings and their moons to better understand their formation and their evolution. And we're always looking for signs of life anywhere we can. And I'll be going through all of these examples in detail in a moment as we journey through the solar system. So on our journey, we're going to start from here, well, not here, JWST, kind of Earth adjacent, and slowly make our way out through the different objects that JWST has observed. So this diagram isn't to scale at all. And I'm going to talk in terms of AU when I talk about distances. So distance from the sun, 1 AU is equivalent to 93 million miles. And Earth is around 1 AU from the sun, with JWST being at 1 million miles further. So that's also around 1 AU. So that's the kind of units that I'm going to use to describe it. So the closest objects to Earth that we can observe are something called NEOs, or near-Earth objects. And a small body is considered as an NEO only when it's around 1.3 AU or closer. And a great example is the asteroid system of Didymos and Dimorphos. And Dimorphos is orbiting around the larger Didymos. And JWST wanted to observe these two rocks in particular because they were the target of the double asteroid redirect test, or the DART mission. And DART's aim was to check if we can alter the trajectory of an object in case something ever comes towards Earth. And DART was crashed into the smaller Dimorphos. And this is an image time-lapse here from JWST of around 5 hours that shows that impact. And this was a huge feat for us in the moving target test team because DART was traveling at 110 milliarc seconds per second, which is over 3 times that initial speed limit that we had. So it's only after that extensive testing that we did that this was made possible, or they gave us the green light to actually do it and not break the instruments. So another important milestone was hit with DART. It marked the first time that JWST and Hubble simultaneously observed the same celestial target. So I said they were going to work together. So the images in blue here are Hubble. So the two in the background, the Hubble one and the JWST one, they were taken at almost the exact same moment. And this image in front was taken about 12 days after the impact by Hubble. And this image in the front helped scientists to kind of come to the conclusion that the mission worked and it was a success, and we actually managed to change the orbit of Dimorphos. And scientists are also interested in the tail on the end there and what's happening with that material. They want to know how it moves in space, its composition, in order to better understand what's happening inside these objects. And this marks humanity's first time purposefully changing the motion of a celestial object and the first full-scale demonstration of asteroid deflection technology for planetary defense. So it was a really, really big thing that we managed to do, and JWST helped with that. Then we continue our journey. We're now out at 1.5 AU from the sun, our closest neighbor, which is Mars. And we have a lot of landers and orbiters at Mars, but for JWST, what we really want is the big picture. We want to be able to have a global perspective of the planet. And so it took these maps back in September last year. And this left image shows a surface reference map. And then the 2 NIRCam instrument fields of view are over the top, where we have these NIRCam images on the right. And Mars is one of the brightest objects that JWST is allowed to view. And so it was amazing to get images and not just a white screen from these. So it was an amazing achievement to get them. And we also use NIRSpec for Mars to do spectroscopy. And that told us about dust and icy clouds and what kind of rocks are on the planet's surface, and also the composition of the atmosphere. Then traveling out from Mars, we hit the asteroid belt between 2 and 3 AU, which is home to most of the asteroids in the solar system. It's also home to one of the dwarf planets, Ceres, and a handful of the most exciting main belt asteroids have been observed with JWST, but only one so far has made the news, and it's this one because it was so small. It was actually during commissioning that scientists noticed something photobomb one of their MIRI test observations. And so they asked themselves, what is this? And realized that it was only 100 to 200 meter in diameter. rock that had photobombed them, and it's really, really tiny. It's one of the smallest ever detected in the main belt. And asteroids, like the one we saw before, are made of like metals and rocks, whereas comets are mostly ice and dust, and they have that characteristic coma or tail. And comets aren't usually found in the main belt because it's too hot. Ice doesn't do well when it's hot. So we thought that ice would melt there and we wouldn't find anything like this, but we managed to look at something called a main belt comet. This one is 238P Reed, and it showed us something completely unexpected. So on the left is an artist's illustration of what it might look like with all that ice and dust vaporizing due to the heat of the sun. And on the right is the actual JWST image and the spectrum. And the image shows us that distinctive halo and that tail, and the spectrum shows us that, yes, it is in fact water vapor that's present. So scientists are trying to figure out how comets like this can even exist. And we've already seen a lot. So we've only made a dent so far in the solar system. We are already at 3 AU, just left the asteroid belt, and we've just entered into the home of the outer planets, the giant planets. And our next stop is Jupiter, which is a distance of just over 5 AU, so 5 times the distance of Earth from the sun. So Jupiter is the largest and one of the brightest and most challenging objects to observe with JWST. And a team of scientists called the ERS, or the Early Release Science Team, they've got the very difficult job of testing all of the instruments and all of the instrument modes on everything they can in the Jupiter system to test whether JWST can do the science that it needs to do in the solar system. And that's where these images come from. And they also work closely with citizen scientists like Judy Schmidt, who processed these images herself. And NASA deemed them so good that they used them all in the press release. And the team have been characterizing Jupiter's cloud layers, winds, composition, temperature structure, and even its auroral activity using JWST. And we characterized the rings and are looking more closely at the moons as well. This is some very recent science by that team, and it used the high-resolution imaging of NIRCam, and we're able to track individual jets at different altitudes using the NIRCam high resolution. And that's inside a newly discovered jet stream feature. So inside that white box, that white band is a newly discovered jet stream feature. And by tracking them, they figured out that this jet stream travels at about 320 miles per hour, which is around twice the speed of the winds needed to categorize a hurricane as a category 5. So really, really strong winds. And this work was published in Nature Astronomy just in October of this year, so just a couple of months ago. And another recent publication that happened was about Europa. Europa is a special type of moon called an ocean world. And we call it that because we think that under a great crust of ice, ocean worlds have these deep subsurface water oceans, and they may have the recipe needed for life to occur. So when JWST observed Europa, it detected carbon dioxide in a specific region on the icy surface, and they think that that carbon dioxide came from the ocean itself. So the graphic here shows a map of Europa's surface with NIRCam in the first panel, and then compositional maps from NIRSpec IFU in the next 3 panels. So the white pixels here correspond to carbon dioxide in different forms. And we humans are carbon-based life, so any detection of carbon in a water-based environment is a great sign that the environment might be habitable for life as we know it. So it's a big step to be able to find these chemicals. Then we have the other large moons of Jupiter. Ganymede, the largest Galilean moon, is on the left, and Io is the most volcanically active. And the top images are some close-ups from the Galileo and Juno missions to Jupiter system. And the bottom images are from JWST. So the ERS team have also been observing these larger moons as well as smaller ones. And that's a spectroscopic map of Ganymede, and it shows the light absorption around the poles, which says that there's probably this detection of the molecule hydrogen peroxide. And we think that this is from charged particles around Jupiter and Ganymede impacting the icy surface. And this image here on the right is of Io, showing several ongoing volcanic eruptions. These hot spots are current volcanic eruptions. And it's the first time also that they've been able to link a volcanic eruption with these forbidden transitions of gaseous sulfur monoxide. So traveling out to 9.5 AU, we arrive at Saturn. You might be able to see it a little bit better on the TV screens, people in the room. This NIRCam image is targeting the whole Saturn system. So we can look at the rings, we can look at the moons, and we can look at the atmosphere as well. And although the Cassini spacecraft observed the atmosphere from closer up, this is the first time we've been able to look at this particular wavelength, which is 3.23 microns, and it's unique to JWST. So scientists have been using MIRI to figure out why there's that dark feature at its North Pole, which you might be able to see on the screen more. And they're also using the long exposures of this image to look at the fainter, more diffuse rings that we don't see when we see Saturn. And like Jupiter, Saturn also has some really interesting moons. This is my favorite moon of all time in the solar system. It's Titan, Saturn's largest moon. Titan is the only moon in the solar system that has a dense atmosphere, and it's the only body where there are rivers, lakes, and oceans, like on Earth, but instead of being made of water, they're made of methane. And Titan had this amazing press release with these two left images from JWST NIRCam. And on the left shows one filter highlighting the atmosphere, and on the right shows a composite of different filters. And you can see the clouds, you can see albedo changes on the surface. One of the lakes, Kraken Mare, is thought to be like a methane sea, and Belette is composed of dark-colored sand dunes. And after seeing the clouds, scientists kind of wanted to see again, because clouds change and move. They wanted to see how they change and move. So 30 hours later, they used the Keck telescope, which is a large ground-based telescope in Hawaii. And this right image is from that observation and shows that the clouds are still there, but they've changed shape and changed their positioning a little bit. So that helps scientists try and figure out why Titan is so unique in the solar system. Another one of Saturn's large moons is Enceladus. We also put it in the same group as Europa as being one of these extremely interesting ocean worlds. And scientists using JWST recently discovered this giant plume jetting out from the south pole of Enceladus as a result of it having that subsurface ocean. And this jet extended more than 40 times the size of the moon itself. And this animation shows how the plume feeds the moon's torus and supplies the rest of the Saturnian system with water. Paused a bit. Oh, well. And how do we know it's water? We've used near-spec IFU capabilities, so those image cubes, to isolate the pixels that have the plume. So it's highlighted here in purple. And when we extract the spectra from just those pixels, we see that there's obvious water features. So those peaks you can see in the spectrum. And this is how we suspect that a lot more water in the Saturn system comes from these Enceladus plumes than we initially realized. And it leaves this giant water torus or water donut around the planet. So in irregular orbits between Jupiter and Neptune, you sometimes get these weird things called centaurs. They're half comet and half asteroid, like the mythical centaur is half human and half horse. And so past Saturn, but before we reach Neptune, we've run into the centaur Chariklo, which is between 13 and 18 AU. So what's so special that we wanted to look at it with JWST is because it went through something called an occultation. And even though it's 160 miles across, so quite small, it has rings. And an occultation is a type of eclipse where an object travels between us and a star, and it allows us to measure the light from the block star to find out more about the object. And the left video here shows Chariklo moving across the star in the center. And the right graphic shows what happens to the star's light. So it's very similar to how we study exoplanets. And it was a very close call, but unfortunately we missed Chariklo itself by a hair. But we did get its two distinct rings. And this is really redefining the different classes of small body in the solar system, because we're realizing that small bodies can have these complex features like rings and moons, and they're not as simple as just being a rock floating around. Then out at 20 AU, we finally hit my favorite planet, which is Uranus. And it's my favorite because it's the weirdo of the solar system, and it's the only planet tilted on its side. It also appears to be much colder than it should. So it contains a lot of mysteries. And this is a 2-color composite from February of this year. And it looks at the planet for a total of just 430 seconds of exposure time. And with just that, we can see the rings, the moons, the clouds, all beautifully clearly. But there is still a lot of science to be done. So look out in the very near future for any more Uranus images that might come out. And we can get hints of the kinds of exciting things to expect from future data. If we zoom into this a bit, we can see the blurs in a lot of places. We expect to see some of the smaller moons. And scientists are also excited to look at detail in the rings. The cloud features tell us a lot about circulation and weather and deep chemistry and that faint polar structure that you can just about see in this image. Usually needs a lot of exposure time to see, but we're seeing it in just that 430 seconds of exposure time, which is amazing. And that actually wasn't the first time that we looked at Uranus with JWST. More observations happened with MIRI and NearSpec beforehand in January. And it's annoying I can't share any of the actual data with you now, but I can share these models that we generated before launch. And that allowed us to plan ahead for actual data analysis. And we generated synthetic data cubes in the resolution and the wavelength range of the MIRI IFU. So these data cubes of Uranus. And each pixel in that image has a spectrum of a similar resolution to the one above. And spoiler alert, the images that will come out eventually look very, very much like this. In fact, I thought I was accidentally looking at a simulation rather than the real thing when I saw it. And we might lose some spatial resolution with this, but what we lose in spatial resolution, we gain in spectral resolution. So it is worth it. And to make up for the fact that we lose some of that spatial resolution, we use other telescopes like Hubble to do, and also ground-based telescopes like Keck, to look in the visible and the near infrared at the same time, so we can know what's going on at these higher resolutions. And it was a very successful campaign, and the science will be coming soon. And if we keep going out, we get to Neptune at 30 AU. And this was the first time we pointed JWST an ice giant. So it was the most exciting day for me this past year. And you can see Neptune with its amazing rings and its largest moon, Triton, also. And with the planet on the background of galaxies, you really get a sense of kind of the scale of the universe. And these images were taken as an outreach-only program. So it wasn't for science purposes, even though people are now using them for science. It was literally just to showcase the NearCam's capabilities to the public. And I was very privileged to be the subject matter expert for this, and the Uranus image also that you saw before. So I worked with Space Telescope Science Institute to get them ready for public release. So we look a little bit closer, and remember, we're all the way out at 30 AU. So the time it takes for Neptune to go around the sun is 164 years. And my favorite fact is that it's so distant in the time that we've had telescopes, modern telescopes that are good enough to take photos of Neptune. We actually haven't seen enough time pass to view the North Pole. We've never seen the North Pole of Neptune. And so when I first saw this image, I didn't even think I was looking at Neptune. I thought I was looking at Saturn, because we hadn't seen the rings like this since the 80s when the flyby happened with Voyager 2, which is the last time we went to the ice giants. And we're clearly seeing 7 of 8 of the moons that are in the field of view. And in the atmosphere, we're also seeing a lot of features. And Triton, which is Neptune's largest moon, in that top corner, is actually considered a small body rather than a moon. because we think it's a captured object from the Kuiper Belt rather than a natural moon. Some other details you may have missed in these. Not only can we see the rings, we can also see the faint ring arcs that are in the top left there. These are clumps of dust and rock that travel around the planet like a moon would, but they appear as bright areas in the rings. You can also see the faint inner gal ring, and also Naiad is visible there. And Naiad is only 60 kilometers in diameter. Remember, we're looking at 30 AU and we're seeing something that's 60 kilometers in diameter, even in this short exposure. And the right images here show the atmosphere in different wavelengths, and the bright areas are methane clouds and reflected sunlight, and the darker areas are looking at deeper methane emission. And scientists are using these images to do science, even though they were only meant to be used for outreach. You can't stop scientists. So we just passed Neptune and we're into the domain of the small bodies now. From 30 AU out, we're in the Kuiper Belt. And Kuiper Belt extends from 30 to 55 AU and contains these Kuiper Belt objects, or sometimes they're called trans-Neptunian objects, or TNOs. And KBOs are much colder and further away than asteroids and comets that are near the main belt. So that makes them much harder to observe, but it also means that JWST's capabilities are the most advantageous for them. So a lot of JWST time was devoted to Kuiper Belt objects. My friend Ian, my colleague, he had a really hard time with how many objects he had to observe. The picture here shows the size comparison of the largest known KBOs compared to the Earth and the Moon. You might have heard of some of the dwarf planets, especially Pluto and its largest moon, Charon. And a lot of the ones on this graphic have been observed by JWST. And as I said, I've lost count. I think Ian also lost count. But over 80 different Kuiper Belt objects have been observed already. And this has allowed scientists to start classifying them in different ways to gain more information about how their different colors are and their sizes and their compositions. And none of this was doable before JWST. And just as a last slide, I can't leave you without mentioning the most exciting thing that's happening in the future. So the Uranus Orbiter Probe was prioritized by the Planetary Decadal Survey. And this will be the first dedicated mission to an ice giant planet. As I said before, we haven't been back since Voyager 2. So that was the first and last time we actually visited these planets. And it was just a very fleeting flyby. And they're the last unexplored class of planet in the solar system. So this is a really, this is an ideal timeline. And by ideal, I mean very optimistic and completely surreal. But if we started development next year in 2024, it would be about 7 years of development, etc., until launch, because we want to make the most of something called a Jupiter gravity assist that only happens at certain times and makes things more efficient. And that's available in 2031. So if we launched in 2031, it would take around 13 years to get out to 20 AU, where Uranus is. And it would arrive at the system in 2040s. And the scientists met up in California in the summer of this year to start discussing these kinds of things. And hundreds of scientists and engineers came, and it was really exciting to see how behind this mission the science community is. So look out for mentions of it in the future. And I will leave you with a summary. And thank you. Looking forward to your questions. Shall I turn on this light? Oh, people online.
Hello. There we go. Hi. Okay. So we do have time for questions in the room. We're going to take questions on Zoom and on YouTube as well. I'm going to turn up some lights in here. We already have a question. We're going to have Sam, who's our new communications officer at the RAS, who's going to help with the mic. Thank you, Sam. Yeah, there's a hand.
Yes, thanks for the talk. Does the focus have to be adjusted for different objects in the solar system? In other words, is it different from distant objects to near objects?
There are a lot of engineering things that they have to do in that JWST control that I do not understand. They have to, so the way it works is that you send in kind of what your object is and a projection of where it will be, and then they will calculate for you whether they can get it or not in the time frame that they have, and what guide stars they'll need to be able to get it, and then it all goes from there. And I don't know the minutiae of how they actually manage to get that data, but it's magic. We can take one online if you want.
Okay, wonderful talk. Thank you so much. I have Anna online who says, absolutely brilliant talk.
Thank you.
So accessible without compromising the academic / hard science stuff much. A couple of questions from Zoom. Kang asks, what is the difference between observing objects in the mid-infrared and near-infrared range? And why do these differences arise?
Yeah, so the actual observation, mid-infrared is a lot harder. It all come down to the fact that near-infrared is closer to the visible. So we've got a lot more kind of technological advances in the near-infrared. And when you get to the mid-infrared, you get a lot more noise. So as you're entering into infrared, it's heat, and heat is a very difficult thing to get rid of. It's in everything. You have to go down to absolute zero to be able to get rid of any heat. So there's always going to be noise. And the further you go into the infrared, the more noise there is. I hope that answers the question.
I have one from YouTube as well. And if you do have questions in the room, please do raise your hand and we'll keep a lookout. Matthew is curious to know, well, first he says, thank you for the talk. Curious to know what's the difference between Jupiter's great red spot in JWST image and Neptune's great dark spot in JWST's image?
Great question. Yeah. So we're still kind of learning about what the great red spot is and why it's been going for so long and how it changes over time. That was a big part of the JWST's science for Jupiter. So there's a whole entire program looking at just the great red spot. So that's how much we want to know about it. Then great dark spots. I mean, the atmospheres of Jupiter and Saturn and Uranus and Neptune are very different. They have similar qualities. They're both giant planet types, but the difference between a gas giant and an ice giant is very large when it comes to composition, and that changes everything about how these storms are created and the kinds of chemicals that you find in the storms and how they move. Also, the temperatures are different. And even between the two ice giants, Uranus and Neptune, we do find great dark spots or dark spots at Uranus and at Neptune. It's not just that great dark spot that we've seen. We've seen lots of others, but we still don't understand really what's happening in these dark spots at the ice giants because we haven't been there and we haven't been able to figure it out. Yeah, it's still a mystery really, and that's a great question for a thesis topic at some point in the future.
Hint.
Yeah.
We've got quite a couple of questions on Zoom and YouTube still. So, but again, if you have any questions in the room, please let us know. Eris on Zoom wants to know, in your opinion, what is thus far the most promising in terms of rewriting science books discovery of JWST? Has there been any?
Rewriting science books, goodness.
From new discoveries or new data from JWST. Maybe it hasn't happened yet.
Maybe. I mean, they're always looking at lots of amazing things in the astrophysics. I can't keep up with how much they keep doing in the astrophysics community. They are constantly discovering some new thing to do with black holes and all sorts of things, and it's really amazing. But in planetary science, I would say that the most groundbreaking thing they've done, I think, is the Kuiper Belt object stuff, because we didn't really know how different Kuiper Belt objects were, like what makes one Kuiper Belt object different to another. And they're actually creating these bins for different types of Kuiper Belt objects now. And that will probably be something that will change the textbooks in the future, because you'll be like, oh, what kind of Kuiper Belt object? Instead of just saying Kuiper Belt object, it'll be, you know, this type and this type. Like we didn't have the ability to find out the types before. So I think that's really groundbreaking.
Yes, that is. That's amazing, actually. I didn't realize that.
Mm.
Andrew from YouTube is asking, what will be the main focus of future solar system work for JWST?
The main focus, there's lots and lots of main focuses for the future. A lot of people are very interested in ocean worlds and these icy moons because of how much we can get from what's happening in the subsurface oceans using infrared. So a lot of JWST time will be dedicated to the ocean worlds, more than would be to other moons, for example. Then there's also the Kuiper Belt objects. As I said, there are just so many of them, and we've never been able to look at them before. So my colleague Ian, who still works at NASA, has got a lot of things coming up.
And kind of a tack on to that question, which is something I can't remember about JWST. It's an issue with other telescopes who have begun and then run out of fuel or coolant or whatnot. How long is JWST expected to perform?
So it was only meant to last around 5 years. It had to last 5 years, and with the hope of it lasting 10. But because the ESA launch went so well, they realized that so the limiting factor of it is that the fuel runs out, and then you can no longer point the telescope where you want it to, because the fuel is what's pointing the telescope. So if you can't point it anywhere, then it's not a telescope anymore. That being a major factor, we thought we would only have maybe 15 years of fuel, but we have more than 20 years of fuel. So that means that in the future, the thing that will probably stop us from being able to use JWST won't be the fuel. It will be some other failure that will happen due to its age.
Wow. I mean, that's amazing, because, I mean, you were just mentioning how many different things they're going to want to look at.
Yeah.
It takes fuel to keep changing its position.
Exactly.
That's going to use up a lot of fuel. So it's really amazing that.
Yeah. 20 years of fuel is a lot of fuel.
Okay. More questions on Zoom. Akash asks, are refractions or scattering by ISM taken into consideration while transmitting data? And how are these errors minimized?
So when I showed that image of the focused star, you can see like a pattern. So like it looks like a star, and that's because it has a diffraction pattern that is unique to JWST. So if you look at the Hubble diffraction pattern, then it's like 4 spikes. Whereas JWST, because it's hexagons that it's made of, it's got 6 spikes. It's very unique to the telescope, and it's something that scientists all around the world, especially a space telescope, are constantly trying to figure out how to model it so that they can cancel it out from other observations. So it is an ongoing scientific battle to get rid of these diffraction patterns, etc.
I have a couple more questions. Again, checking the room if there's any hands up. I don't see any. Oh, do we have a hand in the back?
Thanks, Naomi, for a great talk.
Thank you.
I was really interested to hear you talk about images made for research and how scientists overcame obstacles to still use these images for doing scientific research. So what are the limitations of an observation that's been made for outreach, and how can scientists still usefully use those observations?
Yeah, so a major limitation is access. These images are usually put in some kind of lockdown so that they can't be used for a certain amount of time. But once that has been lifted, it's free for all, basically. But a lot of these outreach images are chosen for their color contrast rather than for scientific goals. So it depends, it's just luck as to whether a scientist would have use for the filters that they've chosen, because it's not chosen for any scientific use, it's just chosen to make the most beautiful image.
Last one from YouTube here, which is an interesting question. kind of similar to the Hubble Deep Field. They're asking, does the James Webb Telescope make gravitational lensing photos and how? And I think when JWST did its deep field image, we got a bit of gravitational lensing, but it's not, you know, if you want to take a stab at it.
Yeah, it does. It takes these images of like the deep fields that it does that Hubble did. One of the like first images they released was one of these deep fields, and you can see the galaxies like being duplicated and lensed by these gravitational fields and by massive clumps of stars and the gravity of those stars. So you do get these. I don't know how the astrophysicists actually use that to calculate things. That's too much maths for me, but yeah, it's all very interesting.
Yeah, and if people online are wondering what does that look like? Well, if you get a wine glass and you put it on text or something and you move it over and you look at the bottom of the wine glass, how it deforms text or images, that's kind of that gravitational lensing that you can see in some of those images from Hubble and JWST.
Yeah.
Last question from Zoom. I hope you like this because you said Titan was your favorite moon.
It's my favorite. Yeah.
That's a moon question from Zoom. Erin asks, well, first they say, wonderful talk, thank you.
Thank you.
Do we expect JWST to discover any new moons? Oh, exciting.
Yes, we do. So part of the Saturn and Jupiter projects is to use NIRCam, which is that high spatial resolution camera, to see if we can look at the differences in two images and maybe find something that's moving that we didn't think was going to move. And that's kind of how we discover these new moons. We've done it with Hubble before. They've discovered new moons of Saturn with Hubble. So the same kinds of things are going to happen with JWST. We're just waiting for the data to be processed because it takes a lot of processing, and it also takes a lot of exposure time to be able to get these really small objects. So yeah, hopefully in the future, new moons will be discovered by JWST.
So last chance for any questions in the room. Oh, there's one. Yeah, there it goes.
Right, thanks for the talk. Just wondering why there's so much security around the images that when you first get them, why they're not just released straight away.
Straight away, yeah. So when we get them, they're usually in a specific file format that is not very accessible. So they come in something called a FITS file, which is not even, you can't even open it on a normal laptop. You have to download something special. So we can't just go straight from that file and release them to the public. But even before that stage, they go through a process that is, it kind of refines the images and gets rid of any of the dead pixels that might be on the instruments. There are lots of very like fine-tuning type things that happen. It's an automatic process usually, although you can take it back and do it yourself. But scientists don't want to see the raw image usually, unless they're trying to look for something specific. They want that finished one. And then if you want to get to the stage when you've got that beautiful image of Uranus and Neptune, you then have to start stacking different wavelengths on top of each other, which is something that I wouldn't be able to do. It's probably something Lucinda could do because it's like Photoshop, etc., and things like that they need to use to be able to create the best contrast and things. So there's lots of different stages in between getting the raw data and getting the science out of it.
Yeah, one more question about that.
Not sure this is relevant. I just wondered, could the JWST, could the JWST somehow be used to look at our own Earth? We've seen about climate change and things, how it could.
Good question. Unfortunately, because of the fact that it's looking at heat, Earth is extremely hot. And if it that's what the shield is for. So the shield is to stop the heat from the sun getting to any of the telescope. So we don't want it getting on the mirror. We don't want it getting to the instruments. Like nothing, we want it to get hot. We want it to be as cold as possible so that we get rid of some of that noise from the heat. So we can't turn the shield away from like into the sun. So that's our only limitation. We can't look at anything towards our own sun. And unfortunately, Earth is hot and also it's towards the sun. So we can't look at Earth, we can't look at Venus, we can't look at Mercury. Yeah.
Thank you very much.
No problem.
So just to let everybody know, we've done some remote observations on Jupiter using that image. We did it live and collected data live from JWST. And then that was on a Friday, and the following Monday, we got to see the data imagery. So you can go to our RAS YouTube channel. It's called Eyeing the Ionosphere. We're looking at the atmosphere of Jupiter. And then we've looked at Uranus as well. We were studying the magnetic field through remote observation via the Keck in Hawaii, which is all done live over like 3 days. And it's a lot of fun because it's astronomers, all remote. It's astronomers in Mauna Kea working on the observatory. And then, of course, then we get to kind of see what we're looking at and understand the science behind it and the research behind it. I want to thank you. Thanks you, Dr. Naomi Rowe-Gurney, for your talk today. Thank you so much.
Thank you.
We'll give her a round of applause and thank you. Thank you all. And a pleasure having you. And we'll just wish everyone a happy winter break, happy holidays, and a happy new year. And we will be having another talk in January. It will be online only. It will be poetry and science communication. So I hope you all join us then. Thank you for coming. Bye-bye.
You're welcome to come in the library on your way out. We've got some books on planning and